Howdy! Welcome to Aspire Mountain Academy. I am Professor Curtis, your instructor for this course in Introductory Statistics. In less than 10 minutes, this video describes the requirements and the test statistic used when conducting hypothesis testing on a population standard deviation, or variance. Let's get started. So we've got two main requirements we're going to satisfy here because there's two assumptions upon which our methodology rests. First, we need to have a simple random sample, and second, we need to have a normal distribution. Notice that there's no out here with the central limit theorem, so we can't use central limit theorem to approximate the normal distribution. We've got to have a normally distributed set of data values, or there's no go with this, period. The reason for this is that the chi-square test statistic is not robust against departures from normality. Basically, all that means is that, in order for the test to work well, you've got to have a normal distribution. So it's going to be pretty strictly enforced requirement here that, this test isn't going to work too well if you don't have a normal distribution to start with. Let's look at our example problem here, involving the heights of supermodels. So here we've got 10 ladies and their heights were measured, and here you see the actual heights in the table there. So we've got 10 of them, and we're using a 1% significance level because the thought is that the heights of supermodels have much less variation than the heights of women in the general population. So we're going to use a smaller significance level so we can pick up at smaller variation in our test. And the heights of the supermodels are claimed to have a standard deviation less than 2.6 inches. So there's our problem. Let's go ahead and test this claim with our hypothesis testing method and see how this pans out. First, though, we have to check to make sure our two requirements are met. Problem says we have a simple random sample, so there's the first requirement. And second, we dump the data there in the table that you saw into StatCrunch and go ahead and make a QQ plot to check for normality. And it's not perfect, but yeah, it's fairly good. So we're going to say, yeah, we're normally distributed. We've got the second requirement. We're good to go with our method. So we start by looking at the claim. The claim is that sigma, the population standard deviation, is less than 2.6 inches. And then now we're ready to actually write our hypotheses. So the null hypothesis, as always, a statement of equality. The alternative hypothesis, we just adopt the claim to represent our alternative hypothesis because there's no semblance of equality with the claim. So we can just adopt it, make it our alternative hypothesis. The problem statement gave us a significance level alpha of 1%. So that's what we're going to use. And the most relevant statistic for testing population standard deviation is going to be the sample standard deviation. Now, this might surprise you because the standard deviation is a biased estimator. It doesn't target the population standard deviation. So why would it be the most relative statistic? Well, if you'll recall the method that we used for confidence intervals of standard deviation, then you'll remember that we actually went there. The route we took was through the variance. And the variance is an unbiased estimator. We're going to do the same thing again here with hypothesis testing. We're going to go through the variance. And so therefore, because we're going through the variance, which is a unbiased estimator, then we can say, yes, go ahead and take our sample standard deviation as the most relative statistic for our test on the population standard deviation. We're now ready to calculate our test statistic, and you can see this is how we're going through the variance. So we've got the degrees of freedom multiplied by the sample variance divided by the population variance. So we can put numbers in for that. Degrees of freedom is just one less than the sample size. We've got 10 ladies in our sample, so 10 minus 1 gives us 9. And then we take here we're taking the sample standard deviation and squaring it. That gives us a sample variance, but we could have calculated the sample variance all the same. We have the actual numbers. So either way works. Notice we're putting 2.6 in for our population standard deviation. That's the claimed value that we have up here. Remember that when we do hypothesis testing, we're doing it under the assumption that the null hypothesis is true. So under that assumption, we're going to take 2.6 and use it as the value for our population standard deviation. So that's where that number comes from. And now we've got all the numbers in, so we just punch that out on the calculator, and out comes our test statistic, 0.852. Now we're ready to make our decision. Do we reject H0 or do we fail to reject H0? To do that, we can compare the p-value with the significance level. Here's our significance. Here's the actual test value right here. So our p-value is coming out really, really small. And you remember that the test statistic is a boundary for the region that is the p-value. So we have a left-tailed test. That's what we get from our alternative hypothesis. So it's this little area right there on the left. You can barely see it, so it's so small, but that's where it's at. Making the comparison with alpha, we're definitely going to be inside that region of rejection. Therefore, we reject the null hypothesis. Alternatively, we can compare the test statistic with the critical value. So here's our critical region right here. And you can see that this area for the p-value is definitely smaller than the area for our level of significance, alpha, the critical region. So that's how we're inside the region of rejection. We get the same thing when we look at the test statistic. The critical value is the boundary for this area of rejection. So the critical value comes out 2.088. That's the boundary here on the right side of that shaded area there. So we go ahead and actually compare that with our test statistic, 0.852. So 0.852 is definitely going to be to the left of that. So we're inside the region of rejection. Therefore, we reach the same conclusion. We're going to reject the null hypothesis. So because we reject the null hypothesis, we're going to conclude there is sufficient evidence to support the claim that the standard deviation of the heights of supermodels is less than 2.6 inches. Notice where each part of his statement comes from. So there's sufficient evidence because we rejected the null hypothesis. We support the claim because it's a one-tailed test. The rest of the statement is just a rehash of the claim itself. And that brings us to the end of this mini lecture. I hope you found it helpful. You can find more mini lectures for this and other courses at AspireMountainAcademy.com. Thanks for watching. I'll see you in the next video.